Alright, time for another physics video presentation. I probably should turn this light on. Alright. Anyway, sorry. Production failure on my part. So comments are nothing really. The Perf Action guy did post a link to a video, but it's on pair production and entanglement and blah 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 blah. Which is just the Three Bears story, and they just add something like, well, and the Three Bears went to Walmart, and bought a water filter and blah 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 blah. I mean, it's sorry, they're just making up a story based on little tiny shreds of evidence, and none of it makes any sense. So the part of this argument is this difference between having some sort of math thing and having some sort of mechanical thing. So it's like you could argue like a watch. A watch has moving parts, mechanisms that are perfectly arranged in such a way as that it predicts the future, in the sense that it gets the time right in the future. It knows what time it is in the future, so to speak. It predicts it very well. What time it will be at a specific time, it'll tell you the right time. Because it's a model, it's a mechanism, that's modeling the reality. It's doing a specific thing in a specific order, and that specific thing correlates perfectly with the mechanisms of the universe, and therefore it can predict the time. And there's no math required, no blah 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 blah. So yeah, I don't know. So I'm just saying there's just so much to say, in the sense that they don't have a model. They say there's these anti-atoms, existing, and anti-particles, but the idea of an anti-atom just doesn't make any sense. Okay, the protons, the positive charge on the outside, and it's in a bunch of material with a bunch of atoms that have the negatives on the outside. That's not going to work. They're going to annihilate. How do they avoid it? They can't make a model of it, is my point. They can talk about it being the way it is, but they can't draw you a picture of it and show you how it's possible that it could possibly work that way. It's not possible. Yet they just keep telling you it's the truth. It's not possible for them to draw a picture of it, show you any mechanism that allows this to be true. Anyway. Then this comment I didn't understand at all. I mean, I suppose I could read it. I keep thinking there to be some value in putting a magnet inside a plastic shell to keep the iron filings from falling into the magnet. Why would there be value in it? As opposed to the usual tabletop flat sheet of paper, etc. I don't know. Is there some reason all you're doing is saying you're not going to let the filings get to the magnet? And so you're going to suspend them in some area and say how much force is there and how much will they align with that force. So you're going to get the same result. In the sense you can create some patterns because of the arguments I've already made about the new magnets being created opposite each other. And therefore they're going to repel each other. So you won't accomplish much. Trying out different magnet shapes, spherical shells, other shapes. I don't know what shapes would help, in the sense that all you're doing is making the field weaker and stronger then by changing the distance from the magnet. So I don't understand. The flat surfaces below the magnets are like cross-section slices, single images of a CT scan. Okay. But again, the cross-section of what? Again, you're forcing something to be in a condition that's not its natural state. A CT scan isn't stopping your brain or whatever's getting scanned from doing what it is going to do. There's no mechanism forcing it to give you a fake image. I'm just saying the image you're getting from iron filings is not the image of the forces. It's an image of the effect of the forces. Anyway, so I figure, I would have liked to have done this Sean Carroll video, these biggest idea crap, and I first looked at it, I said charge, that's a great subject. It really should be, at least, it should be 1 or 2, right? I mean, charge is everything, really. It is the fundamental mechanism of the universe is the fact that there is charge. Charge creates the repulsion and attraction. The whole mechanism is really, charge is almost everything. But no, it's change, which is really uninteresting, and calculus. And so it's just this idea that we can use a certain math trick that really isn't all that great a trick, frankly. I mean, it doesn't really save you that much work. So this is another example where it's, theoretically, okay, calculus is really good if what you want to know is there's only two variables. It's like this times this. You only have an x and a y variable, and then you can project something way into the future and you don't have any complications, and it's really nice. But it just kind of totally fails when, no, there's going to be a lot of variables. There's lots of things that are affecting something, and you're not going to have no straight path. And all calculus is saying is that, we can mathematically do this. We can mathematically understand something as a bunch of bits, pieces. And then we can take all of those pieces and we can line them up over here and add them up and subtract the ones that are, opposite each other. And we can do a formula and get equals. But you're only going to do that by taking all these pieces, all these different little data points, and to make your average, like you want to know the average of this line, to make an average you have to cut it into all these little slices and figure out what each slice is doing and then do the average. So it's still a lot of work when it just might be easier to make a model, make a physical model, cut the pieces of paper or something along the lines, and then cut your little square and then just measure the mass of the two pieces. That'll tell you the area of this space versus the area of this space. So I mean, you might be able to do it just quicker by making yourself some kind of mechanical model and then just cutting and weighing. That may be easier, quicker, frankly. So it's not a miraculous thing. It's not, they make it out like it's doing some sort of magic. It's, again, all of these things can be done lots of different ways. You never have to use one of Maxwell's equations. You can use the equations that preceded Maxwell and get the right answer. It's just that Maxwell's equations are a little more efficient. And that's it. It doesn't, it really isn't, all of this stuff is just geometry and algebra and blah, blah, blah. It's not, there's nothing, well, whatever. It's not, some sort of discovery of some great, without it, essential thing. It's just, again, just taking some of the waste out of the process of getting an answer. Making it less complicated. Less complicated, tricky word. So anyway, I did find these Understanding Physics by Dave. They're pretty bad videos, frankly. I mean, I could have done a couple others on momentum and velocity where he said things that were just silly, like, when a satellite is getting pushed by gravity, it's doing work. Gravity's doing work. But somehow when it's pushing a human, it's not doing work. I mean, some kind of silly thing like that. Just nonsense. I mean, poorly done. So, no offense, but yeah, the videos kind of suck. So I figured I'll play this one because I played a minute and a half of it and it had some suck in it. So I wish I could make it louder, but I can't.
Information about nuclei from something called electron scattering.
Electron scattering. Let's see if there's any hope of getting more volume out of this damn thing. This video is really low. I don't think this will work, but I'll do it anyway. Let's see if there's anything better.
And in electron scattering, what happens is that electrons behave like waves, and they produce diffraction patterns.
Okay, electrons behave like waves and produce diffraction patterns. So here he uses an image of a simulation of water. Okay, it's just a simulation. And he's going to say this is diffraction. These wave lines are diffraction. When what we're really talking about is just the spreading. All right, the the pattern is obviously just a matter of the frequency going in. There's nothing special there. And diffraction is just scatter in all directions, theoretically. And then so this is diffraction of a laser light by a circular aperture. So this is the whole thing. Now he says here you get the same pattern when light falls on a small sphere. Well, you really don't get the same pattern because the amount of light is so small that actually does do the diffracting in, and that's the part you need. And all you really get is that little Argo spot. You get the little, you get the one spot where all the photons are hitting the same exact location, and therefore you can see that location because there's enough light reflecting off it. Where all the other lines that are still there, you're never going to see them because they're spread over so much surface. You just don't get enough photons. Diffraction is happening at the edges. Yeah, well, of course. The rest of it is opaque. So yes, it has to happen where it's not opaque. And so again, this is a surface argument. It's really not an argument about slits. It's an argument about surfaces and what surfaces do to photons. And so they mix and match electrons and photons as if they're the same thing when they're fundamentally different, and blah, 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 blah. I just don't know what to do about the volume. I just don't have any other way to amplify it.
So let's remind ourselves about diffraction. If we have plane wave fronts going through a slit, then they diffract, and the slit acts like a point source.
Right, so the slit acts like a point source. It's, you know, there's no point in talking about it as if it's a point source because it's not. But you know, it's and we know in water waves, why is it happening? It's happening because the water is adhering to the surfaces. It's sticking. It's friction, and it's slowing down. And so that water, okay, is tied to all the other water molecules. The water themselves is sticky, so the slow ones are slowing down the fast ones, and you end up with a wave, an arc that comes out. It's a known physical phenomenon, and we know that photons aren't doing the same thing, so why talk as if it's the same thing? It's not the same thing.
If you have waves like light from a laser going through a circular aperture, in other words a little hole, then we get a diffraction pattern as well.
No, you get an interference pattern. So again, it's not a diffraction pattern. It has to be called an interference pattern if you're going to be at all accurate or fair or any of those good important words. It's just not a diffraction pattern. It's an on-off pattern. It's not just light spreading. It's light spreading and then only being visible at certain locations. So again, I'll argue, a simple over and over again argument, that all you're doing is reconstructing photons where your path lengths are within the same phase. So you change the phase, you break pieces of photons, and then you reconstruct them. But there is no destructive interference. So he's just basically saying, I have a small aperture, I make a hole, it doesn't matter. But so it's not a slit, it's a hole instead, and I shine light through it. And the light ends up creating what's going to be big giant arcs, but let's just say lines of on and off, you know. And all that's telling you is that off these surfaces there'll be photons that go to these different locations, and the photons that from one surface that match the distance from another surface, they're two different places, so they're two different distances, and where those distances are a wavelength different, a full wavelength difference, you have a hope of reconstructing a photon. And where they're not, there'll be no photon. There'll be a photon. So it's just about the fact that you're taking photons, and the slit itself is going to break some of them, and they're going to and therefore you're going to try to recombine a photon that has the pieces in the right order. So one's missing this piece and one's missing this piece, and if you put these two together, you'll end up with a photon. And that's really all that's really happening. So there's places where you reconstruct the photon and places where they end up still broken. Places where you reconstruct, places where they're still broken. And that's all that's really happening.
Well, we get this thing called an airy disk.
So he said you get this thing called an airy disk. I just wish I could do something with this volume. Yeah, let's see. Maybe the mic was broken or something. Maybe the speakers are off.
Okay, we get a blob in the middle, and then we actually get maxima and minima.
Blob in the middle.
Maxima and minima, I'm not particularly bothered about here.
So why we get maximum mimia, he's not particularly bothered about here. You know, it's only the fundamental part of the pattern. But whatever.
But interestingly, if you shine laser light on a pinhead, on a small sphere, you get a very similar pattern of maxima and minima. Diffraction happens at the edges, and then
so again, so diffraction, they're just going to use a word, and they're always going to turn it into a wave function type word, which doesn't make any sense. Diffraction doesn't. The frequency you see when the straight lines are going through is obviously just frequency. And somehow you're converting that into this round pattern. Well, how would it make any sense? Because some of those photons haven't gone through the slit yet, right? I mean, if there were waves, you'd say, well, this wave is different than this wave, is different than this wave, because those waves that haven't gone through the slit yet. How can you see them all at one time when they haven't even gone through the slit yet? You know what I'm saying? So the pattern is continuous, and always, no matter how many waves I put through, I get the same wave pattern. So it just doesn't make any sense to say, to correlate it to the frequency. The only correlation is the distance difference. So if one side is a full wavelength longer distance away, then there's a hope of reconstructing the photons back in order again.
interference happens as well.
Some kind of interference happens as well. Some kind of interference. I mean, it's just so useless a statement.
We get these maxima and minima, and there's an equation that we don't need to know. If you do need to use it.
So there's an equation we don't need to know, so you can use it. Sine theta for the minimum is 1.2 wavelengths divided by the aperture size, which is they're calling B. Yeah, that's a standard for I don't know what that standard is for. That's got to be for a specific wavelength, this 1.2 thing.
And it's an angle for the first minimum. Sine theta min is approximately 1.2 lambda over B. Lambda is obviously the wavelength, B is the diameter of the circular aperture, the hole, or the sphere. Okay, and theta min is the angle.
Well, there's no distance here to obviously the size of this thing will change with the distance, so I don't know exactly what angle for the first minima. So he's just saying what's the angle that the light comes out as. Okay, so that's a little, it's not telling you because you're not putting the distance into the equation, so it's not going to tell you its size. It's telling you what angle the light comes out. So obviously at different distances, the same angle will be a different size.
Angle for the first minimum. Now, experiments have been done with very high energy electrons.
So experiments have been done with very high energy electrons, he says. So this chart doesn't make any sense at all. It says number of electrons going up this way. Then it has scattering angle going the other direction. And these are for different materials that you use to scatter it with. So each line is, one is oxygen, one is like xenon or something, and the other one's some other thing. So it's just not a pattern. It's worth figuring out what the hell he's even talking about here, what they're measuring. So the number of electrons clearly would indicate the more electrons you send through something, you could argue the more you're going to disrupt the atoms, the more heat you're creating. To move the electrons, you have to be pushing them with something. So you're pushing them with sort of little gamma rays and whatnot that you have to be pushing the electrons with. That's also going into the material. And so, yes, depending on how much of these electrons, how many you shoot into the material, you'll get more scattering. The fewer is what that looks like. So the fewer electrons, the more scattering. I don't know, it doesn't make intuitive much sense, but you could understand that the more rigid the material stays, the more likely it is the atoms will dictate which way the electrons go. And the more electrons you have, the more they're going to dictate how much the atoms move. So, you can make all kinds of arguments about how velocities of bullets will change how the object is degraded. How well the bullet just flies right through the substance if it's a very high velocity, or whether if it's a slow velocity it starts to degrade and break up and do a lot of different things that can cause even more damage. That demonstrates nothing about anything called interference or diffraction. The fact that there's a change based on how many electrons you shoot in or how fast the electrons are going, yeah, that's certainly something you could expect.
Using particle accelerators, these electrons have a lot of energy.
So again, they associate, it's fine to say they have energy, but what they do is they turn this into voltage and frequency. Electrons don't have a frequency unless, of course, you shoot them in pulses. But they have their velocity is not a frequency. And they always want to convert everything into this idea that frequency is intrinsically momentum, when it isn't intrinsic, it isn't fundamental. Obviously, higher frequency means more often. And more often means usually in the same space, more of. So obviously there'd be more energy associated with higher frequencies, but it's a conditional statement. I mean, it depends on the context.
And they fire them at nuclei of different isotopes. And what we notice is that we get minima. In other words, diffraction is happening, and we are getting a similar pattern to the one that we just talked about.
Okay, it's not in any way similar, really. There are 3 different kinds of isotopes with 3 different patterns, and clearly the pattern, I would argue, is just a matter of, you could think of it as like a magnet. You could have a magnet, and you could put it at an angle, a little bit of an angle, turn it a little bit at an angle, and then you could shoot electrons at it. And the truth is the electrons are going to bounce off one side and do something different off the other side. So it's going to turn the magnet. And the more electrons I can throw at it, the more likely I'm going to get the magnet to flip or change its orientation to be more compatible with the flow of the electrons. So you could see lots of reasons why different atoms will react differently to how many electrons you throw at them.
We're getting a minimum. The electrons behave like waves, and at a certain angle, theta min, we can measure this angle, and the angle depends on the wavelength of the electrons.
So again, they don't have a wavelength, they have a momentum, they have a speed, a velocity. That's the key function. It's not a wavelength, it's not a frequency, it's a velocity. So they're destroying the word velocity and pretending that velocity equals frequency, and it doesn't. Electrons aren't photons.
We find it also depends on the mass number of the isotope, because that will be something to do with its radius.
Yes, how big the isotope is, how big the atom is going to change how well electrons are deflected by the electrons of the isotope. You could just even argue that how dense how many electrons the isotope has and how densely packed they are will dictate how electrons deflect off the electrons. And they're mostly going to deflect off of electrons. I mean, which ones ever get to the nucleus to do something? Well, then they're going to also interact with nuclei, and then they're going to split atoms in half, and they can do all kinds of things. So, this is, so again, they're not going to show you how this could mechanically. They're not going to show you a diagram of the atoms and the isotopes, and then show you a diagram of the electrons going through, because then they have to say, well, the electron is superimposed, it's in two places at once, and it's affecting two different atoms at the same time, and some other kind of nonsense. And it'll be nonsense. They don't have a mechanical mechanism. They don't have a model of this.
Okay, high energy electrons from particle accelerators fired at elements in the gas state. We get diffraction patterns produced. Why high energy electrons? Well, we want the electrons to have a wavelength of about 10.
So they're saying high velocity electrons, and they just won't. They say high energy instead. No, it's a high velocity electron, and again they're saying let's convert that into a wavelength, and so they're saying we want to give the electron a small enough wavelength so we can make correlations between electrons and photons, and it's just nonsense, frankly. They're not doing the same thing. They're different things. They create patterns for different reasons. Photons and electrons do not create pattern for the same reason.
To the minus 15, because that's basically what we're looking at. We're looking at the nuclei. It's the nuclei which is producing the diffraction pattern.
Well, again, they have no. That's his guess. That has nothing to do with an actual proof of any kind. So just he says it, he can say it, but he hasn't demonstrated it. There's no evidence that's conclusive that, oh, you hit the nucleus. You don't have any evidence of that.
Well, the wavelength of the electrons should be about the same order of magnitude, so about 10 to the minus 15 meters. Okay?
10 to the minus 15 meters, which 10 to the minus 15 meters. Yeah, not minus 15 meters. So, smaller than, the typical, obviously much smaller than the typical wavelength of a photon.
We get lots of data using different isotopes, electrons with different wavelengths. We plot a graph of the radius cubed against the mass number, and we notice we get a straight line. The radius of...
Says you, but fine. Demonstrated by what?
The different nuclei cubed is proportional to the mass number. R cubed is proportional to A. Therefore...
Yeah, all atoms are made out of little bits. Like you'd almost argue they're all made out of hydrogen. We already know the quantum rules. So clearly there's going to be a proportion. No matter how big or small the atoms are, they're going to have a proportional effect, and that proportional effect will always end up drawing a straight line because all atoms are made of the same thing.
The radius is proportional to the cube root of the mass number, or R equals R naught A to the third, where R naught is a constant. So, firstly, why should this graph be a straight line? Why should R cubed be proportional to A? Well, the radius cubed is proportional...
Because because there's a correlation between, volume and density and mass. There are all ways of measuring a similar thing. I don't know, that's not exactly that. There's always going to be a proportion because the function of the electron and proton and their ability to attract and repel is a standard amount of ability. And so no matter what form you put them in, there's always a standard amount of charge in the atom.
Proportional to the mass number. In other words, the radius cubed is proportional to the number of particles in the nucleus. And this isn't surprising because the radius cubed is also proportional to the volume. If it's a sphere, then 4/3 pi r cubed. The radius cubed is proportional to the volume, so the volume of nuclei is proportional to how many particles there are in it.
Right. So this is totally unmiraculous and in my frankly uninteresting.
The more particles it has, the bigger the volume it has. And that seems very, very logical. It follows, therefore, that nuclei have the same density. And we'll discuss that. That will be important shortly. So,
Well, the function of a nucleus is the same. Now, whether all nucleuses are the same, it seems reasonable to assume that whatever process is allowing protons and electrons to cohabit, protons and neutrons, same difference, means that standard arrangement is probably a standard size, and so then nucleuses are really standard in the sense that you just put more bits in, the nucleus just gets proportionally bigger based on the more volume you've created, and that's it. Where the electrons in the orbits can be much different. They don't have to obey the same standards because their ability to act on the charge is based on the inverse square law and their repulsion to each other.
all nuclei, like water droplets, have the same density because mass divided by volume, A divided by R cubed, is constant. Okay? R naught in this equation, R equals R naught A to the third, is the value of R when A equals 1. Now, if A equals 1, then we're talking like just a proton. So R naught is the radius of a proton, or a neutron. So if we plotted a graph of R against...
Okay, so my only argument against this is something we already know, right? We know that hydrogen is the most buoyant atom, and then helium is the next buoyant, and down the list. So there's a certain correlation, but we know that as atoms get heavier, they're obviously getting more dense. So whatever the separation is between electrons and protons, that is the size of hydrogen, is the distance between electron and proton is allowed to be larger in the hydrogen atom than it is in all the other atoms, because as they get more consolidated, that distance between electrons and protons shrinks, because you're multiplying the effect of charge by putting it in smaller spaces. So as you consolidate the charge, it has more potential. It creates a difference in distance. I guess that's the only way to say it. But this is sort of just a buoyancy argument. So I didn't know it was going to go this abstract. Well, let's see what else he says.
A to the third, the cube root of A, then the gradient of that graph would tell us the radius of a proton. And if you do that, you get about 1 times 10 to the minus 15 meters. That is the radius of a proton.
Yeah, it says whatever, blah, 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 radius of a proton. They have to interact. So, again, this is the figuring out the density of the proton. Figuring out the density of an atom is one thing. Okay, figuring out how far electrons are from protons. But to sit there and say you can figure out how big the proton itself is, I think is really reaching.
So, what holds the nucleus together? We have protons and neutrons. The protons are both positively charged here, if this was a helium nucleus, and they are repelling each other. We can work out the repulsive force between them, F equals K Q1 Q2 over R squared.
Right, and that's if there's nothing else in the equation. You're just saying, well, let's figure out how much they are repelling, but we're not going to consider the fact that they're arranged. There's a specific arrangement that allows them to stick together.
And if we work out the repulsive force, we get about 58 newtons. This is absolutely huge when you bear in mind.
Right, so this is the part where they don't have a model, so therefore they can't understand that the strong nuclear force is actually not a strong force. It just has to do with the fact that you're mitigating the force. So the obvious fact is that if you understand that neutrons decay into a proton and an electron. So I'll just draw the electrons as smaller and the protons as bigger. So if you know that's already happening, well, I can always do the color thing. You already know that's happening, right? Okay, so now you're adding another proton or two. So let's just say we add 2 more protons to this equation. Well, there's an arrangement you can make between them where you could understand that the protons, if they got between an electron, they're attracted, not repelled by electrons. So they're both attracted to the electrons. Yes, they're repelled by each other, but they're attracted to the electron. So even if you know it from that simple basic step, you can understand how these 2 protons, one piece of the neutron and the free proton, let's just call this the neutron, that just that mechanism alone would undo the negative effect, because now you have a pull combining with your push, however you want to, push with your pull, or a pull with your push, and so you're equalizing the pressure. So whatever pressure there is between the 2 protons, it's being mitigated, it's being changed by the existence of the electron. And I would argue that's happening because the electron is displacing the pressure between the protons by pushing it out, and therefore it can't reflect between the protons anymore because it's leaving the building. So you can understand why 2 protons can get very close together if there's an electron between them. Not that complicated. A lot closer together than they could get if they were just free protons. And the same thing's happening to electrons sticking in atoms. They're a lot closer to each other than they would be if they were just electrons. If there was no nucleus in the center full of protons, the electrons on the outside would all fly away because they don't like each other. But obviously there's another force that's telling them it's okay. So if you're talking about a net force, there's obviously no net force between the protons because of the mitigating electron.
This is between 2 protons, 2 tiny little particles, and the force repelling them is about the weight of an average cat. It's a massive force.
Right. So again, that's if they ignore the fact that these things are arranged, in pairs. So you have a neutron. Let's see, neutron. What do I do with the? I guess I dropped it. I guess I don't see it. So I could see. So you could just have 2 pairs, right? You could have a neutron. It's not chalk. You could have a neutron here, and then with another proton, and then you could also have, like I say, a bigger nucleus could have another. So this is the proton, this is the neutron, and then you could just have the same arrangement over here, okay, where you just stagger them. So you now have another electron here, and so now you can make patterns. Just by putting the neutron in another place. So I could just have the neutron here, and then I could have it'd probably be better to have them crossing each other, right? Yeah. So I could put the neutron here and then put another proton here. So I can have 2 protons and 2 neutrons and create a system where they're bound to each other. So these 4 protons can get much closer to each other because there's these 2 electrons that are allowing them to mitigate their repulsion. Blah, blah, blah. Lots of geometry possible. But there's only 100 atoms, 100 elements, so it's kind of demonstrating that the number of geometry isn't, so only certain geometries are really stable.
Something must be holding them together, some kind of a super glue. Some other force must be gluing them together.
Right, some other force must be, so it's the system is basically push-pull, that's what magnets are doing. They're either attracting or repelling. So well, if their repulsion is being stopped, then they obviously don't have this tremendous power to fly apart from each other. then there must be some other force doing it. It must be some of that pull stuff. It must be what magnets are made out of. The same mechanism. So you've created a circumstance where there's equal amount of pull as there is push, and therefore the protons don't have to go anywhere.
And that force is the strong nuclear force. Here are some facts about the strong nuclear force. It's very strong. It acts on protons and neutrons.
It's just as strong as the charge force. Or the north side of the magnet is just as strong as the south side of the magnet. So to say, oh, the only way you can compensate for this north side is to have some strong force, very strong. No, it's exactly the same force.
It has a very short range. Its force carriers are called gluons. Okay, how do I know it's very...
Yeah, how do you know any of that's the truth? Yeah, that's right, you don't. You just made that up. Your model sucks. You can't draw a picture of it. It doesn't make any sense. It's junk.
Very strong? Well, it has to be. These two protons are repelling each other massively, and the strong nuclear force...
Right, but again, the massiveness of two repulsing magnets is completely annihilated, right? I have two south ends, they hate each other. Well, if I just stick a north end right in between them, no problems anymore, right? Problems solved. The strong repulsion between the two south ends is completely annihilated by just sticking a north end in between.
This is holding the nucleus together. It must be like Velcro holding it together.
So again, it just has to do with the idea that you recognize that not 50%, but 1/3 of a nucleus is electrons. You know, it's for every proton and neutron. So let's say we had an equal number of neutrons and protons. Well, then you know that half the neutrons are electron and proton, right? So then you can double the number of protons. So you have twice as many as the atomic number of protons and 1/2 that number of electrons. So it still has a half more protons than electrons. So it's still decidedly positive because there's a half more protons than there's twice as many protons as there are electrons. But that's the real answer.
On protons and neutrons. Okay? This tells us why neutrons are needed for stability. Neutrons are needed because they act as superglue which holds the proton.
Yeah, so again, they know that a neutron is a proton and an electron, so they already know that. They already know it's a dipole, and so all they have to figure out is that, yes, they have two south end magnets, and all they need is that electron end to stick in here. Now they have 3 south ends, but it'll all stick together very well because it has that one electron in between. That's all I need. I just need the one north side, right? I mean, you could. I don't have to explain this, do I? So theoretically, you could understand that if I have two magnets facing this way, and the red ends are here, right? And I stick another magnet in, okay, with its green end in between, and its red end is going to be sticking out here, right? So this is the neutron, right? This is a proton, this is a proton. You can kind of get the idea, right? So you just have to understand there are such a thing as a magnetic monopole. It's in the form of electrons and protons, and this configuration is stable. That's all you need to know, is that, yeah, this will work. You put one whole magnet between two positive monopoles, and you'll end up with this perfectly. These things should be flying apart, but they won't as long as that thing's stuck in the middle of them.
And they also act as spacers to kind of keep the protons away from each other as much as they can. So neutrons...
But again, as much as they can, they understand that the nucleus of the atom is tiny. So they're obviously not separated by much space. They're smaller than hydrogen atom. They're small, 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 the nucleus. Tiny little thing.
Too many neutrons, but enough neutrons are needed to kind of provide the Velcro needed to hold the nucleus together. The strong nuclear force has a very short...
So again, it's the exact, it's not doing anything but just providing the opposite. So where there is push, because they're repelling each other, you're just introducing the pull, the thing that does the opposite thing. So you're just doing the negative positive charge thing, that they'll get very close to each other. Opposite charges attract.
range. So, again, like Velcro, the nucleons only attract their neighbours. The strong nuclear force only has a range of about 1 times 10 to the minus 15 metres. And this explains what...
So let's understand. So now they're saying, oh, I've got all this repulsion between these parts. Well, we took away the repulsion by putting them in the right geometry. So there is no repulsion. So that's why they say it declines so quickly, is because, well, they're saying there's all this repulsive energy, but the fact is it doesn't really exist. The north sides of the protons aren't trying to fly out. So yes, they display no will to do so, and therefore this force doesn't have any range, because the repulsion doesn't exist. Essentially, it's been completely compensated for by having the mitigating particle in the middle.
Nuclei all have the same density. If the strong nuclear force had a bigger range, then bigger nuclei would be pulled in tighter and they would have a larger density.
Right, so the nucleuses are proportional in the sense that they're all doing the same thing, that same mechanism of two south sides, and you just stick the north side in between. That always has the same density, the same size, the same spatial, it occupies the same space. So all the nucleuses are made out of the same thing.
But that doesn't happen. Why? Because the nuclear force has a very short range. Nuclei only attract their nearest neighbours. Force carriers, we'll talk about that when we talk.
So again, it's sort of silly to say it, because obviously the range of the positive charge of the entire nucleus is substantial enough to keep the orbits, to keep the electrons in their positions. So there's no weak force of the actual positive charge. So he's saying there's some other thing. He's almost trying to say that the strong nuclear force is some other kind of force besides just positive charges. It's just the repulsion between the protons, including the protons that are inside the neutron. So again, why don't they just eliminate this neutron character and understand it's a dipole? The neutron isn't a non-polarized particle, it's a dipole.
Talk about the standard model. We don't need to know a great deal about them, but the force carriers for the strong nuclear force.
I mean, a neutron is theoretically neutral, just like a magnet is theoretically neutral, except if you're close enough to tell which side is north and south. So from a distance, it's neutral, but close up, it's not neutral, clearly.
Okay, let's look at this graph. We've looked at it before, we'll look at it again. And it's a graph of N against Z. It's the ratio of neutrons to protons. And it tells us that for smaller nuclei, if you let's say up to calcium, then roughly the number of neutrons is the same as the number of protons. The ratio of neutrons to protons is about 1 to 1. If you look at heavier elements, then the ratio of neutrons to protons is about 3 to 2. So bigger nuclei need a lot more neutrons to...
Right, so that would just be something you could sort of understand, that if I'm doing this kind of mechanism, that as I reach out, as I go further and further, as I make more and more of these stick to each other, that is, I have another one over here and another one over here, right? Just alternate the greens and the reds, that as I go further and further out, this time let's just do it this way. Right, so I'm just making the thing bigger and bigger, that I'm going to need more of the electrons in proportion to the protons to be able to go out further and further to make a shell, if I want to keep that shell positive. Alright, so well, let's just finish this off since we started it. Again, sorry about the volume.
Why is that? Because there's lots and lots of protons repelling each other. We need lots and lots of superglue.
Right, so lots of protons. Right, well, the number just has to do with the circumference, you know. So you could sort of understand that if you're making something spherical, that the circumference is going to be more complicated to hold together, the outside of the shell, than the inside. The outside not only has to stick to the inside, but the outside pieces have to stick to them, each other. And so you would need more electron bit to deal with that problem. So you need more electrons to protons in ratio. So it makes sense.
And we need lots and lots of neutrons to kind of get in the way of the protons to kind of keep them apart.
So again, he says to keep them apart. No, you're allowing them to get really close to each other. You're not keeping them apart.
Okay, for small nuclei, it's about 1 to 1. For very large nuclei, then we need lots and lots of neutrons. Why? The neutrons provide strong.
It's not lots and lots. It's just 50% more for the bigger atomic nucleuses, and they're the ones that are unstable. The more unstable they get, the more you dilute the process with extra neutrons.
Nuclear force, and they act as spaces between the protons. Later in the topic, we'll use this graph, in fact, to explain lots of different things. It's a very important graph, and we'll explain why certain nuclei are stable and others are unstable, and whether they're going to emit beta plus or beta minus.
Alright, well, he's just talking about what kind of radiation you're going to get out of an atom that based on how this configuration is put together with these neutrons. And like I said, the more disproportion you have with this pure geometry of 3 and 3, and you end up with this fourth extra, or you end up with an extra electron, the more the more extra bits you have, the more like you could argue that it would become less and less stable a structure. So it's like 5 and 10 and 15 would work for some structures, and if you go 14, it's not stable, and 13 is even less stable, and then 12 is a little more stable. But it's only on those certain numbers that you have more stability, just because of the geometry. That's probably enough said on that. Alright, so it's not much to work with there. But anyway, all of these subjects just illustrate they don't have a physical model. They don't have, like I said, they'll never draw you a picture of any of the, here's the photon, here's the interaction, here's the thing, all you'll get is maybe a Feynman diagram or something, something so rudimentary that it doesn't say anything about process. Because their model is incoherent. It's a bunch of disconnected themes and ideas that they just have tiny bits of evidence for. So this whole story, this whole Three Bears story of going to, it just has to do with the fact they found a bear print and a bowl of porridge and a Walmart receipt and a cigar, and and they said, what does this mean? And this is the story they wrote out of these little tiny pieces. And it's it's got the obvious weakness of just a story. They haven't proven any of this, and they certainly haven't shown how the model works, how the footprints were created, how the porridge was created, how the bears got into Walmart. Anyway, so till the next time and such, so forth and whatnot. Just call it a video. Probably not the most useful. Again, sorry about the volume. Couldn't do anything about it.